Hello everyone. Before starting the lesson, try this warm-up. It takes about 30 days to go from one new moon to the next new moon. In case you don't know, a new moon is when you are standing on the earth, you look up in the sky, and you don't see any moon. That's what a new moon is. You see 0% of the moon's surface. Now, if you're standing on the earth and you look up in the sky and you see half of the moon's surface, 50% of the moon's surface, that's the first quarter. A full moon, you're seeing 100% of the moon's surface, etc. Okay, so that's the lunar cycle. So I want you to complete the graph below. Percent of moon visible, number of days. Start with a new moon on day 0. And complete the graph for the rest of the days. So pause the video and see if you can make this graph. So this is how I made my graph. On day 0, I see a new moon, so 0% of the moon is visible. It says it takes about 30 days to go from one new moon to the next new moon, so 30 days later, I am at a new moon again. Now, halfway through this lunar cycle, I see a full moon. So halfway, that would be 15 days, I would see a full moon. That's 100% of the moon's surface visible. Now, I'm doing this for 2 full cycles. So new moon, 30 days later, a new moon. 30 days later, another new moon. There's also 30 days between full moons. They just happen halfway through the lunar cycle. But this is how I can figure out what the graph looks like. Now the points here and here, when I'm at the first quarter and the last quarter of the lunar cycle, when I see 50% of the moon's surface, that's going to be halfway between the full moon and the new moon. So 7.5 days. So every 7.5 days, I'm a quarter of the way through the cycle. Now, the lunar cycle is an example of a periodic function. So we're going to interpret graphs of periodic functions using proper terminology in this lesson. Now, there's a special kind of periodic function which is called a sinusoidal function. So we're going to relate details of sinusoidal functions to their graphs as well in this lesson. So we're going to talk about some terminology, then we're going to talk about properties of sinusoidal functions. So we'll start off with some terminology, and these would be good to have written down on your unit summary sheet. First off, periodic function is a function that has a pattern that repeats at regular intervals, like the lunar cycle. It went up, it went down, it went up, it went down. That same pattern was repeating. The word periodic means repeating, repetition. Hence the periodic table of the elements in chemistry. We have repeating patterns of properties in different elements. Whereas here, a periodic function, the function has patterns that repeat over and over again. A cycle is one complete repetition of the pattern. The period is the length of one cycle. The axis is the central line between the maximum and the minimum values. And the amplitude is the distance between the axis and the minimum or maximum values. I'll illustrate these with an example, but make sure you have them written down first. So here's my example. This is the same situation as we graphed in the warm-up, the lunar cycle. Here we have the percent of the moon visible and the number of days on the x-axis. So I'm going to go through the period, the axis, the maximum, the minimum, and the amplitude, so you can see how those definitions relate to an actual function. So first off, let's talk about a cycle. One complete cycle would be from here to here. I know that's one complete cycle because now that exact same pattern repeats again. I could also say there's one complete cycle from here to here, because after this point, I get the exact same pattern repeating. So the period is the length of one cycle. So if I look at how long one cycle is, I can start from here and go to here. That's one cycle, it's 30 days. Or if I looked from here to here, well, that's from 15 days to 45 days. That's also a span of 30 days for one complete cycle. So the period is 30 days. Now the axis, the definition I had on the screen before was the axis is the central line between the maximum and minimum values. Well, the maximum value on this function is 100, the minimum value is 0, and so the central axis is going to be halfway between the maximum and the minimum at 50. So I'm not just going to write 50 here, I'm going to write the equation of this line, which would be y equals 50. So the period is 30 days. That means one cycle of this function takes 30 days. The axis is y equals 50. That's the halfway point between the maximum of 100% and the minimum of 0%. The amplitude had a definition, the distance between the axis and the minimum or maximum values. So if I look at my central axis, how much higher do I have to go to get to my maximum? Well, 50 units up. Or I could look at it as, how do I move from the central axis to my minimum value? I also have to move 50. So either way you look at it, that's the amplitude. The amplitude in this case is 50%. Now, notice I wrote percent for these values. That's because those are the units I'm using on my y-axis. Just like here for the period I wrote days because that's the units I was using on the x-axis. Period is the length on the x-axis. Amplitude, maximum, and minimum relate to values on the y-axis. So this might be a good example to have in front of you so that you understand what the period, the axis, the maximum, minimum, and amplitude are when we talk about other functions. Here's another example of a periodic function. A Ferris wheel has a radius of 10 meters. When you get on the Ferris wheel, your height is 0 meters above the ground. That just means you're standing on the ground. So I have this picture of a Ferris wheel just so we can imagine what's going on here. We get on the Ferris wheel at the bottom when I'm standing on the ground. And as we ride the Ferris wheel, our height increases and then it decreases. And then it increases and then it decreases again. So we reach a maximum height and we go back to our minimum height over and over and over again. So this is why it's a periodic function, because our height is going to fluctuate between a maximum and a minimum over the whole span of the ride. Now, I'm not going to graph height and time. I'm going to graph height with the angle of revolution. So when we're standing at the bottom of the Ferris wheel, when we get on, we haven't revolved at all. So the angle that we've revolved is 0 degrees. When I reach this point, halfway up, I've revolved around the circle 90 degrees. When we reach our maximum height, we've gone a full 180 degrees from where we started. Here we would be at 270, here we would be at 360 degrees. And the angle keeps increasing and increasing the longer that we're on the ride. So we're looking at the total angle of revolution. Now when we make a sketch of this graph, we're going to want to include not just a drawing of what the graph would look like, but also some values on our height axis and on our angle of revolution axis. Now we do have some information up here. We know the radius of the Ferris wheel. That's important. So we can use that when we're figuring out the heights that we should have on our height axis. Pause the video and complete a sketch of one cycle of this Ferris wheel ride, and then see if you can figure out the period and the amplitude. So let's start with the sketch. Because I know the radius of the Ferris wheel is 10 meters, think about, what that means. From here to here, from the middle of the Ferris wheel down to the outside of the circle, that's 10 meters. So when I've rotated to this point, I'm going to be 10 meters up in the air. When I've rotated to this point, I'm going to be 10 plus 10. That's 20 meters up in the air. So that's how I figured out these values on my height axis. The rotation, well, I'm going from 0 to 360 degrees. I cut that in half, it's 180, and I cut that section in half, that's 90, and then cut this section in half. Halfway between 180 and 360 is 270. So I know every 90 degrees, my height is going to be changed by 10 meters. And that's where I plotted these points from. And then I just attempted to draw a smooth curve through my points. You can see I didn't do the best job with this iPad, but that's the best I could do. So the goal is to draw a smooth curve through these. You're not playing connect the dot with straight lines. You want to flatten out every time you reach a maximum or minimum. So anyway, there's the sketch of the graph. The period, remember what period means? It's the length of one cycle. So we can see one complete cycle on the drawing. One complete cycle is 360 degrees. And the amplitude would be 10 meters. From the central axis to the maximum or to the minimum is 10 meters. So now you've seen two examples of periodic functions, the lunar cycle as well as a Ferris wheel. Now for this next example, we're going to start with an equation. Y equals sine x. So x can have lots of different values. You might recognize some of these angles from our previous unit on trigonometry. But what I'd like you to do is calculate the value of y for each value of x to make a table of values, and then plot those points on the graph. And see if you can make the graph for 2 cycles. So pause the video and try that now. Well, you can get these y values by using your calculator. Sine of 0 equals 0, sine of 30 equals a half, sine of 90 equals 1. You might even remember those as your special angles, some of them. And we can keep that pattern going into obtuse angles. So these values here, if I plot them on the graph, 30 degrees, a sine of that is a half, so I go up to a half, etc. Sine of 90 is 1. I get a graph like this. This is going to be a periodic function. You might also remember the cast rule from trigonometry. For angles between 0 and 90, sine was positive. For values of the angle between 90 and 180, sine was positive. But then when we get into quadrant 3 and quadrant 4, those are our angles greater than 180 degrees, we said sine was negative. And we see that on the graph. We have negative values. Now, I said graph this for 2 cycles. This is just 1 cycle. From here to here would not be 1 cycle because the exact same pattern doesn't start repeating. Instead of going up again, it starts to go down. Here, it would start to go up again. So this, what I've highlighted in a blue rectangle, is 1 complete cycle of this function. So if I wanted to draw 2 cycles, think of it as copying 1 cycle and pasting it right beside it. So here I have the exact same image copied as I did here, and I can see it's matching up nicely. So I have 1 cycle, 2 cycles on 1 graph. I didn't have to recalculate my values. I didn't have to plug in sine of negative 270, for example. All I had to do was copy the exact same cycle right beside. I didn't have to think about where the points went. I already knew where they went because I just counted the squares. So there you have it. You can make a table of values for y equals sine x, and you can graph it, and you'll have a periodic function. Now I'd like you to do the exact same thing with this function, y equals cosine x. So make a table of values, and make 2 cycles on the graph. Pause the video and try that now. So here are the values we get when we find the cosine of these numbers. And this is the graph. So I end up with this graph. That's 1 complete cycle. And to draw a second cycle, I just copy and paste that right beside it. So now I have 2 complete cycles on this graph. Notice it looks very similar to the graph of y equals sine x. It looks like it's exactly the same, except on the y-axis, it starts at a different spot. The graph of sine x started here, and then went up, and then down, and then up. Here we're starting at the maximum and then decreasing. So y equals sine x and y equals cos x look very similar, and we see this same periodic wave pattern. So a periodic function is called a sinusoidal function if it has the curved form of a sine or cosine wave. So if your graph has a repeating pattern that happens over and over and over again, that's a periodic function. But if that pattern that repeats looks like a wave, like the sine curve or the cosine curve, then it's called sinusoidal. That's how you pronounce that word. So all sinusoidal functions have either y equals sine x or y equals cos x as their parent function. Now for the next 2 examples, I just want to show you how you can more quickly make a graph of these functions. So I'm going to graph y equals sine x again without making a table of values. We're only going to use the maximum, the minimum, and the period, and we're going to show 3 complete cycles. So I'm going to model this one, then in the next example I'm going to get you to do it by yourself with y equals cos x. This is y equals sine x. I know that the maximum value was 1, and the minimum value was -1. I know that 1 complete cycle was 360 degrees. So every 360 degrees, I can draw a box like this. So inside each box is going to be 1 complete cycle. Now I know that the sine function starts in the middle, and then it goes up, down, and back up again. So I know I'm starting here. After 1 complete cycle, I'm going to end up in the same spot. So I can plot another point. Halfway in between here, I'm going to be at the same spot again. Now I mentioned this earlier. I know I'm going to start here, but then I'm going to go up, then down, then back up again. So halfway between this point and this point, I'm going to be at my maximum. And halfway between this point and this point, I'm going to be at my minimum. So just to recap, for a sine curve, I know I'm going to start in the middle, then go up, down, and then back up to the same point. So I start here, I end in the same spot. Halfway in the middle, I'm in the same spot. Between here and here, I'm at my maximum, and between here and here, I'm at my minimum. So I don't even need to count the number of squares or anything or look at the scale. I just know the shape of this graph. It's going to go up, then down, then back up again. It's going to reach a maximum and a minimum. Then I just have to draw a nice smooth curve through my points, and I have 1 complete cycle. And if I want to show 3 complete cycles, I just go through the same process again. For my next cycle, I'm starting here, I'm ending here, halfway in between, I'm at the same point, halfway between those 2 points, I'm at my maximum, and halfway between my last 2 points, I'm at the minimum. Then I draw a curve through my points. Now I have 2 cycles. And if I want to make a 3rd cycle, do the same thing. I know I'm going to start and end in the same spot, halfway in between, I'm in the same spot. Quarter of the way through, I'm at my maximum, then I know where my minimum happens, and then I can draw a curve. So there you have it. Just by knowing the maximum, the minimum, and the period, I can figure out what the graph is going to look like and draw a fairly accurate graph. And I can make this graph as long as I want. I can put as many cycles as I want until I run out of space on my graph. So now I'd like you to try this same thing for the function y equals cosine x. Remember what the maximum and the minimum are, 1 and -1, and the period is 360 degrees. It's just that we're starting and ending in different spots in the box that you draw. So start by drawing a box, 3 boxes, plug in your points, and see what you get. So for this one, I know the maximum is 1, the minimum is -1, and the period is 360 degrees. So I've drawn 3 boxes. Now remember, cosine starts at the maximum. Then it's going to end at the maximum. Halfway in between, it's going to be at the minimum. So between your first and your second dot, you're going to be in the middle. And between your middle and your last dot, you're going to be here again. So this is how one complete cycle of y equals cos x looks. Now you can duplicate that process to make the other 2 complete cycles. So there you have it, 3 complete cycles, and it didn't take me very long. As long as I know the maximum, the minimum, and how long the period is, I just need to remember that sine x starts here and cos x starts at the maximum. Then it's just starting and ending in the same spot in your cycle, and you just keep going halfway between the first and the last dot to find the other point, and then halfway between those points to find this point. Once you do that, you draw your curve, and you just repeat as necessary. Now, I want to caution you at this point, if you are working with Desmos, the graphing calculator online, and you're trying to graph these functions using that to check your answers or whatever, you need to be aware that the default setting for Desmos is to have angles measured in radians, not degrees. So if you just start plugging in a sinusoidal function into Desmos and it makes a graph, it's going to look a lot different than the one you came up with because the default is radians. You want to measure your angles in degrees. That's what we're using in this course. So I'm just showing you where to click. There will be a wrench icon for settings. Make sure you select degrees. This is what the screen looks like if you're on a laptop or a desktop computer. If you're using it on your phone, that image might be in a different spot, but you're looking for the wrench so that you can select degrees. Okay, so I just wanted to bring that to your attention in case you're one of those people that wants to check your answers using a Desmos graphing calculator for sinusoidal functions. You need to have it in degrees. And now it's time to practice. So what we looked at in this lesson was what a periodic function is, and then we also looked at a specific kind of periodic function, which is called a sinusoidal function. Sinusoidal functions are waves that you get from a sine function or a cosine function. We will look in more detail at sinusoidal functions in the next lesson, but for now, as long as you know how to make a graph fairly quickly and understand what the properties are, like the amplitude or the axis or the maximum or minimum in the period, then you should be fine. But take your time to practice and then reach out if you need help.